In space, there are monsters so powerful they can destroy entire stars in seconds. We're talking about black holes, places where gravity is so strong that nothing, not even light, can escape. Some of them are small, the size of a city, but the ones we're going to explore today are giants with billions of times the mass of our sun. These space giants can swallow entire solar systems like they were grains of sand. Scientists discovered that some of these black holes spin so fast they distort space itself around them, creating whirlpools of energy that can be seen from billions of light years away. The most frightening part: there's one called TON 618 that is so big our entire solar system could fit inside it thousands of times. How can something so destructive exist? And what would happen if Earth got close to one of them? Subscribe to the channel, leave your like and comment from what part of the world you're watching. Get comfortable and relax. Let's begin. A voyage to the deadliest black holes in the universe. Section 1 of 10. Hello there, and welcome to this quiet place where wonder meets the mathematics of infinity, where science becomes poetry, and where the most terrifying objects in the universe reveal themselves not as destroyers, but as architects of everything we know. Tonight, we're not staying safely on Earth, or even within the familiar boundaries of our solar system. We're venturing into the deepest, darkest corners of space to encounter beings so powerful, so fundamentally alien to our experience, that they bend the very fabric of reality around themselves like gods reshaping clay. These are black holes, not the gentle, distant pinpricks of light we see in our night sky, but cosmic monsters so dense, so gravitationally violent, that they devour light itself, twist time into knots, and stretch the laws of physics to their breaking point. And among them, scattered across the observable universe like sleeping titans, are the deadliest of all. Black holes so massive, so hungry, so catastrophically powerful that they could consume our entire solar system as easily as you might swallow a grain of sand and still hunger for more. But here's what makes this journey both terrifying and beautiful. These cosmic nightmares are not random accidents scattered across space. They are fundamental to everything. They are the sculptors of galaxies, the engines that power quasars brighter than 1 trillion suns, the cosmic vacuum cleaners that regulate star formation across billions of light years. Without them, the universe as we know it simply could not exist. They are creation through destruction, order through chaos, and tonight we're going to meet the most dangerous of them all. Before we begin this voyage into darkness, I'd love to know where you are right now as you listen to this. What time is it where you are? Are you looking up at stars that seem so peaceful and distant? It's humbling to think that as you listen to these words, somewhere out there in that same dark sky, these monsters are feeding, growing, warping space and time in ways that would make the most imaginative science fiction seem timid by comparison. The universe is stranger and more dangerous than most of us ever imagine, and yet here we are, tiny creatures on a small planet, trying to understand it all. If this kind of cosmic exploration speaks to you, if you find yourself drawn to questions that stretch the mind and challenge our place in the universe, I'd be grateful if you could tap like or subscribe. It helps this signal reach other curious minds who aren't afraid to stare into the abyss and ask what stares back. No pressure, of course, just an invitation to join this community of cosmic explorers, people who understand that sometimes the most frightening things in the universe are also the most magnificent. So settle in, perhaps dim the lights if you can, and prepare to leave behind everything familiar. We're about to embark on a journey measured not in miles or kilometers, but in the warping of space-time itself. We'll travel to places where a single teaspoon of matter weighs as much as Mount Everest, where time crawls to a near standstill, and where the normal rules that govern our daily lives simply cease to apply. Our first destination lies 26,000 light-years from where you sit right now, hidden behind vast clouds of gas and dust at the center of our own Milky Way galaxy. It's a place our ancestors could never have imagined, where something with the mass of 4 million suns has been compressed into a space smaller than our solar system. This is Sagittarius A star, our galaxy's central supermassive black hole, and compared to what we'll encounter later in our journey, it's practically a gentle giant. To understand what makes a black hole deadly, we first need to understand what makes a black hole at all. Imagine taking all the matter in our sun, every atom of hydrogen and helium, every nuclear furnace burning in its core, and compressing it down until it occupies no space whatsoever. Not a small space, but literally zero space, infinite density, a mathematical impossibility that somehow exists in reality. This is what physicists call a singularity, a point where our understanding of physics breaks down completely, where the normal rules of cause and effect, space and time simply stop making sense. Around this impossible point, gravity becomes so intense that it creates what we call an event horizon, a spherical boundary in space beyond which nothing, not matter, not energy, not even light itself, can ever escape. The event horizon isn't a physical surface you could touch. It's more like a point of no return, a cosmic one-way street where the laws of physics post a sign that says, "Abandon all hope, ye who enter here." For Sagittarius, a star, this event horizon has a radius of about 12 million miles, roughly 17 times larger than our Sun. That might sound enormous, but remember, we're talking about something that contains 4 million times the mass of our Sun compressed into that space. The density is so extreme that if you could somehow extract a single teaspoon of matter from near the event horizon, it would weigh approximately 6 billion tons, roughly the same as Mount Everest. But Sagittarius A star, for all its impressive statistics, is what astronomers would call a quiet black hole. It's not actively feeding on massive amounts of matter. It sits at the center of our galaxy like a sleeping giant, occasionally snacking on gas clouds or the odd unlucky star that wanders too close, but mostly just existing. Its immense gravitational field keeping the entire Milky Way galaxy rotating in its cosmic dance. To understand what makes some black holes so much more dangerous than others, we need to understand that not all black holes are created equal. The stellar mass black holes, formed when massive stars collapse at the end of their lives, typically contain between 3 and 20 times the mass of our Sun. They're dangerous if you get close to them, certainly, but their event horizons are relatively small, just a few miles across. You could theoretically orbit one safely if you kept your distance, much like we orbit our Sun without falling in. Then there are the intermediate mass black holes, mysterious objects that contain hundreds or thousands of solar masses. These are rare and poorly understood, like cosmic middle children that don't quite fit into our neat categories. Some might be stellar mass black holes that have grown by feeding. Others might be the seeds of something much larger. But the true monsters, the ones that earn the title of deadliest, are the supermassive black holes. These cosmic leviathans contain millions, billions, sometimes tens of billions of times the mass of our Sun. They lurk at the centers of galaxies like sleeping dragons, and when they wake up, when they begin to feed actively, they become some of the most violent, energetic objects in the known universe. The deadliest black holes are not necessarily the most massive, though mass certainly plays a role. What makes a black hole truly dangerous is a combination of factors. Its mass determines the strength of its gravitational field and the size of its event horizon. Its spin rate affects how it drags space-time around with it, creating what physicists call the ergosphere, a region where space and time themselves are pulled into rotation, And most importantly, its feeding rate, how actively it's consuming matter, determines how much energy it's pumping into its surroundings. When a supermassive black hole begins to feed actively, the process is spectacular and terrifying in equal measure. Matter falling toward the black hole doesn't simply vanish quietly into the event horizon. Instead, it forms what's called an accretion disk, a swirling maelstrom of superheated gas and plasma that can stretch for light years around the black hole. The material in this disk is compressed and heated to temperatures of millions of degrees, glowing brighter than entire galaxies. But even this isn't the most dangerous part. As matter spirals inward through the accretion disk, magnetic field lines become twisted and compressed. Eventually, they snap like cosmic rubber bands, launching jets of particles and energy away from the black hole at velocities approaching the speed of light. These jets can extend for hundreds of thousands of light years, carrying enough energy to sterilize entire regions of space. If Earth happened to be in the path of one of these jets from an actively feeding supermassive black hole, the results would be catastrophic beyond imagination. The high-energy radiation would strip away our atmosphere in minutes, boil our oceans, and irradiate the planet's surface to such a degree that not even the hardiest microbes could survive. It would be the ultimate cosmic death ray, and unlike the fictional versions in science fiction movies, there would be no heroic defense, no last-minute salvation. The energy involved is so vast that it dwarfs anything humans have ever contemplated. This is why some black holes earn the designation of deadliest. It's not just their ability to gravitationally shred anything that comes too close, though that's certainly part of it. It's their capacity to project deadly influence across cosmic distances, to reshape entire galaxies, to regulate or halt star formation across billions of light years, and in some cases to pump enough energy into their surroundings to be visible from the very edge of the observable universe. Consider the black hole at the center of the galaxy M87, located about 54 million light-years from Earth. This monster contains approximately 6.5 billion times the mass of our Sun, making it more than 1,500 times more massive than our own galaxy's central black hole. Its event horizon is so large that it could encompass the entire solar system with room to spare. But mass isn't what makes it particularly deadly. What makes the M87 black hole terrifying is its activity level. It's currently feeding, launching a jet of plasma and high-energy particles that extends for at least 5,000 light-years. This jet is visible to our telescopes, a cosmic lighthouse of destruction that has been continuously operating for millions of years. The energy output is so enormous that it outshines the combined light of all 400 billion stars in the galaxy that hosts it. If our solar system were located anywhere within several thousand light-years of this monster, Earth would be uninhabitable. The radiation environment would be so intense that complex molecules necessary for life could not form or survive. Even at our actual distance of 54 million light-years, we can detect and study this object, a testament to its incredible energy output. But M87's black hole, impressive as it is, doesn't hold the record for deadliest. That distinction belongs to objects that exist at the very edge of what physics allows. Black holes so massive and so active that they challenge our understanding of how such objects could even form or continue to exist. As we continue our journey into cosmic darkness, we'll encounter black holes that make M87 look gentle by comparison. We'll visit quasars powered by black holes consuming matter at rates that should theoretically be impossible. Objects so luminous they can be seen from across the entire observable universe. We'll explore magnetars and stellar mass black holes caught in death spirals that release more energy in seconds than our Sun will produce in its entire 10 billion-year lifetime. But perhaps most unsettling of all, we'll discover that these monsters may not be rare cosmic accidents, but fundamental components of how the universe operates. They may be the reason galaxies exist in the forms we see today, the sculptors that have shaped the cosmic web of matter and energy that connects everything from the smallest stellar nursery to the largest galactic cluster. The deadliest black holes in the universe are not just objects to be feared or avoided. They are cosmic architects, creatures of destruction that enable creation, monsters that may be responsible for the very existence of the stars, planets, and ultimately the life forms that contemplate their existence. They represent nature at its most extreme, physics pushed to its absolute limits, and the strange paradoxical beauty that emerges when the universe encounters its own boundaries. As we prepare to venture deeper into this cosmic menagerie of gravitational monsters, remember that everything we'll encounter, every death ray and space-time warp, every impossible density and infinite curvature, exists in the same universe as the device you're using to listen to these words. The cosmos is vast enough to contain both the gentlest planetary sunset and the most violent gravitational maelstrom, both the delicate chemistry of life and the brutal physics of stellar death. Our next stop will take us far beyond our own galactic neighborhood to regions where the normal rules of stellar evolution break down, where black holes grow so rapidly and become so massive that they shouldn't exist according to our current understanding of cosmic history. We'll encounter objects that formed when the universe was young, black holes that may have been feeding continuously for over 13 billion years, growing from stellar mass seeds into cosmic titans that now dominate entire galactic clusters. The journey to understand these primordial monsters begins with a question that has puzzled astronomers for decades. How do you build a black hole so massive that it contains the equivalent of 10 billion suns when the universe itself has only existed for 13.8 billion years? It's a cosmic construction project that seems to violate the fundamental speed limits of growth and accumulation, like trying to build a skyscraper taller than the Empire State Building using only 1 brick per year. Yet these impossible objects exist. We can see them scattered across the cosmos, ancient titans that were already fully grown when the universe was less than 1 billion years old. They lurk at the centers of the most distant galaxies we can observe, their gravitational influence evident in the swirling dance of stars and gas around them, their feeding patterns visible as brilliant quasars that outshine everything else in their cosmic neighborhoods. To understand how such monsters could form so early in cosmic history, we need to travel back in time, not millions or billions of years, but to an era when the universe itself was young, hot, and fundamentally different from the cosmos we see today. This was a time before the first stars had formed, when space was filled with a nearly uniform fog of hydrogen and helium, slowly cooling and condensing under the patient pull of gravity. The first black holes may have formed not from the collapse of massive stars, as the smaller ones do today, but from direct gravitational collapse of enormous gas clouds in the early universe. These primordial black holes would have been born with masses hundreds or thousands of times greater than our Sun, giving them a tremendous head start in the cosmic race to become supermassive. But even with this advantage, growing from 1,000 solar mass seed to a 10 billion solar mass monster requires an almost continuous feeding frenzy that lasts for billions of years. The black hole must consume matter at rates that push against fundamental physical limits, accumulating mass so rapidly that the energy released by the infalling material should theoretically blow away any additional food before it can be consumed. This is where we encounter one of the universe's most spectacular and deadly phenomena, the quasar. when a supermassive black hole feeds at maximum capacity, converting the gravitational potential energy of infalling matter into radiation with an efficiency that makes nuclear fusion look wasteful. It creates a beacon of light so intense that it can be seen across the entire observable universe. The most powerful quasars release energy equivalent to the total output of 1 trillion stars, all concentrated in a region no larger than our solar system. They are among the most luminous objects in the universe, cosmic lighthouses that can outshine their entire host galaxies by factors of hundreds or thousands, and they represent black holes in their most actively deadly phase, consuming matter at rates of several solar masses per year, while simultaneously sterilizing vast regions of space around them. Consider the quasar known as APM 08279 5255, located over 12 billion light-years from Earth. The light we see from this object today began its journey toward us when the universe was less than 1 billion years old, carrying information about conditions in the ancient cosmos. At its heart lies a black hole containing approximately 20 billion times the mass of our Sun, making it one of the most massive objects ever discovered. But mass alone doesn't convey the true scale of this monster's deadly influence. When it was actively feeding as a quasar, this black hole was pumping energy into space at a rate of approximately 10 to the 40th watts. To put this in perspective, this is roughly equal to the energy output of 10 trillion galaxies like our own Milky Way, all concentrated in a space that could fit comfortably within the orbit of Neptune. The environment around such an object would be hostile beyond imagination. Any planet within several thousand light-years would be bombarded by radiation so intense that its surface would be sterilized within hours. The very atoms in the planet's atmosphere would be ionized, stripped of their electrons by the relentless stream of high-energy photons. Even at distances where the radiation wouldn't immediately vaporize solid matter, the constant bombardment would prevent the complex chemistry necessary for life from ever developing. Yet these cosmic death machines serve a crucial role in the evolution of the universe. The energy they pump into their surroundings regulates star formation across entire galaxies, preventing runaway stellar formation that would quickly exhaust all available gas and leave the universe dark and empty. They are cosmic thermostats, maintaining a delicate balance between creation and destruction that allows galaxies to form stars at sustainable rates over billions of years. The jets launched by these feeding supermassive black holes carry this regulatory influence far beyond their immediate neighborhoods. Extending for hundreds of thousands of light-years, these plasma streams carry enough energy to heat intergalactic gas to temperatures of millions of degrees, preventing it from cooling and condensing into new stars. They are cosmic plows, carving channels through space and redistributing matter and energy across distances so vast that light takes hundreds of thousands of years to cross them. But perhaps most remarkably, these deadly objects may be responsible for their own food supply. The turbulence created by their jets and radiation appears to trigger shock waves in surrounding gas clouds, compressing the material until it begins to collapse and form new stars. These stars eventually evolve and die, some of them exploding as supernova that enrich the local environment with heavy elements, while others simply shed their outer layers as they age, providing fresh fuel for the central black hole to consume. This creates a cosmic ecosystem where destruction enables creation, where the deadliest objects in the universe serve as both predator and gardener, consuming matter while simultaneously cultivating the conditions necessary for new matter to form. It's a relationship so complex and interconnected that removing the black holes would likely cause the entire system to collapse, leaving the universe a cold, empty, lifeless place. As we venture deeper into this cosmic menagerie, we encounter black holes that challenge not just our understanding of stellar evolution, but the fundamental limits of physics itself. These are objects where the normal rules of thermodynamics, quantum mechanics, and general relativity are pushed to their absolute breaking points, creating conditions so extreme that entirely new phenomena emerge. Near the event horizon of a rapidly spinning supermassive black hole, space-time itself becomes a fluid, dragged along by the black hole's rotation at velocities approaching the speed of light. This creates the ergosphere, a region where it becomes impossible to remain stationary relative to distant observers. Space itself is flowing like a river, and anything caught in this cosmic current is inevitably swept along. Within the ergosphere, the distinction between space and time becomes blurred. What we normally think of as spatial dimensions become time-like, while temporal dimensions take on spatial characteristics. It's a region where causality itself becomes negotiable, where effects can potentially precede their causes, and where the orderly progression of events that governs our everyday experience breaks down completely. For any material object caught in the ergosphere of a massive, rapidly spinning black hole, the experience would be indescribable in normal terms. The object would be stretched and compressed by tidal forces so intense that individual atoms would be torn apart at the subatomic level. The electromagnetic forces that hold molecules together would be overwhelmed by gravitational gradients, causing matter to disintegrate into its component particles. But even before reaching the ergosphere, any object approaching a supermassive black hole would encounter what physicists call the photon sphere, a region where light itself can orbit the black hole indefinitely. At this distance, approximately 1.5 times the radius of the event horizon, the curvature of spacetime becomes so extreme that light rays can be bent into closed loops, creating ghost images and optical illusions that would confuse any observer lucky or unlucky enough to witness them. The photon sphere represents a kind of cosmic hall of mirrors, where light from distant objects can be bent and twisted into multiple images, creating a surreal visual environment where the same star or galaxy might appear dozens of times at different positions in the sky. It's a region where the normal rules of optics break down, where straight lines become circles, and where the simple act of trying to navigate by visual landmarks becomes impossible. Beyond the photon sphere, as we move closer to the event horizon, we encounter phenomena that stretch the limits of human comprehension. Near the horizon of a supermassive black hole, time dilation effects become so extreme that processes we normally think of as instantaneous begin to stretch out over cosmic timescales. A clock falling toward the event horizon would appear to run slower and slower to distant observers, its rate decreasing asymptotically until it seems to freeze entirely at the moment it crosses the horizon. Yet, from the perspective of the infalling observer, no such slowing occurs. Time passes normally as they cross the event horizon and continue their journey toward the central singularity. This creates a paradox that has puzzled physicists for decades. How can the same event appear to take infinite time from one perspective and finite time from another? The resolution involves quantum mechanics and the fundamental nature of information, concepts so abstract and counterintuitive that they challenge our basic assumptions about the nature of reality itself. The deadliest black holes push these paradoxes to their absolute limits. In the most extreme cases, such as the supermassive black holes found at the centers of distant quasars, the event horizon can be so large that its circumference exceeds that of Neptune's orbit around our Sun. Crossing such a boundary would be like falling into an invisible sphere larger than our entire solar system, a region of no return so vast that light from one side would take hours to reach the other. Within such enormous event horizons, the nature of space and time becomes even more distorted. The singularity at the center is no longer a point, but potentially a ring or more complex structure, creating multiple regions with different causal properties. Some theories suggest that the interior of such black holes might contain entire universes, pocket dimensions where the normal laws of physics are replaced by something completely alien to our experience. But perhaps most unsettling is the possibility that these massive black holes might not be stable objects at all. Recent theoretical work suggests that the largest supermassive black holes might be approaching fundamental limits imposed by quantum mechanics and general relativity. Beyond a certain mass, estimated to be around 50 billion times the mass of our Sun, black holes might become unstable, either exploding in cataclysmic events that would release more energy than the Big Bang itself, or transforming into something even stranger and more dangerous. We have already discovered black holes that approach these theoretical limits. The black hole at the center of the galaxy NGC 4889, located approximately 336 million light-years from Earth, contains an estimated 21 billion solar masses, making it one of the most massive objects ever discovered. If such objects continue to grow, they might eventually reach the point where the fabric of space-time itself can no longer contain them, leading to consequences that could affect the structure of the entire universe. These possibilities push us into the realm of speculative physics, where our best theories offer only hints and suggestions rather than definitive answers. We are exploring regions of parameter space where human experience provides no guidance, where intuition fails, and where mathematics becomes our only reliable tool for navigation. It's like trying to map an ocean using only abstract equations, knowing that somewhere in those mathematical depths swim monsters that could reshape our understanding of reality itself. As our cosmic voyage continues, we'll encounter black holes that exist in states of perpetual violence, locked in gravitational combat with companion stars or other black holes, their feeding patterns irregular and explosive. We'll explore systems where multiple supermassive black holes orbit each other in death spirals that will eventually culminate in collisions so energetic they send ripples through the fabric of space-time itself, creating gravitational waves that carry information about these cosmic catastrophes across billions of light-years. These gravitational waves represent something entirely new in our cosmic exploration, ripples in the very fabric of reality that carry information about the most violent events in the universe. When two supermassive black holes spiral toward each other in their final death dance, they don't simply collide and merge quietly. Instead, they create distortions in space-time so profound that they propagate outward at the speed of light, carrying energy equivalent to the annihilation of entire stars. The detection of these gravitational waves has opened a new window into the universe's most extreme phenomena, allowing us to observe events that produce no light, no electromagnetic radiation of any kind, yet release more energy in seconds than our Sun will produce in its entire lifetime. It's like discovering that the universe has been whispering secrets in a language we never knew existed, and only now have we learned to listen. Consider the collision detected by the LIGO observatories on September 14, 2015, an event that has since become legendary in the annals of physics. Two black holes, one containing approximately 29 times the mass of our Sun and another containing 36 solar masses, had been spiraling toward each other for millions of years. In their final moments, as they approached within a few hundred kilometers of each other, they were orbiting at velocities exceeding half the speed of light. The collision itself lasted only milliseconds, but in that brief instant, The merging black holes converted approximately 3 solar masses worth of matter directly into gravitational wave energy. This energy propagated outward as ripples in space-time, traveling across 1.3 billion years of cosmic history before finally reaching Earth, where it caused the LIGO detectors to vibrate by distances smaller than 1/10,000th the width of a proton. But stellar mass black hole collisions, spectacular as they are, pale in comparison to the cosmic catastrophes that occur when supermassive black holes merge. These events, involving objects millions or billions of times more massive than typical stellar remnants, create gravitational wave bursts so energetic they can be detected across the entire observable universe. They represent the most powerful single events that can occur in nature, rivaling the Big Bang itself in their energy output. The approach phase of such a merger can last for millions of years, with the two black holes gradually spiraling closer together as they lose energy to gravitational wave radiation. During this period, both objects are likely feeding actively, their accretion disks interacting in complex ways that can trigger spectacular outbursts of electromagnetic radiation. The combined system becomes a cosmic beacon, visible across billions of light-years as a hyperactive quasar that flickers and varies in ways that reveal the orbital dance taking place at its heart. As the black holes approach within light hours of each other, their individual event horizons begin to distort, stretching toward each other like two soap bubbles preparing to merge. The space-time around each object becomes increasingly warped, creating complex patterns of gravitational lensing that would make the region around them appear to shimmer and twist like a cosmic mirage. In the final seconds before merger, when the black holes are separated by distances comparable to their own sizes, they orbit each other hundreds of times per second, their event horizons stretching and deforming under mutual gravitational influence. The energy released during this final phase is so enormous that it briefly outshines all other sources of gravitational waves in the observable universe, creating a cosmic scream that propagates across space and time. The moment of merger itself represents one of the most extreme physical events possible within the known laws of physics. The two event horizons touch and instantly merge into a single larger horizon, while the space-time around them rings like a struck bell, gradually settling into the configuration of a single, more massive black hole. The merged object initially oscillates between different shapes, its event horizon expanding and contracting as excess energy is radiated away in the form of gravitational waves. For any civilization unfortunate enough to be located within a few hundred light-years of such an event, the consequences would be catastrophic. The gravitational wave burst would cause tidal effects throughout their solar system, potentially disrupting planetary orbits and triggering massive earthquakes on any inhabited worlds. The electromagnetic radiation associated with the merger, if the black holes were actively feeding, would deliver doses of high-energy photons capable of sterilizing entire planets. But perhaps most terrifying is what happens to the surrounding galactic environment. The merger of two supermassive black holes creates what astronomers call a gravitational wave kick, a recoil effect that can launch the merged object away from the galactic center at velocities exceeding several thousand kilometers per second. This cosmic cannonball, containing billions of times the mass of our Sun, can tear through the galactic disk like a bullet through tissue paper, disrupting star formation regions and potentially ejecting entire stellar systems into intergalactic space. We have discovered several galaxies that appear to have been victims of such gravitational wave kicks. These systems show clear evidence of displaced central black holes, massive objects that now orbit far from their expected positions at the galactic centers. The galaxy 3C186, located approximately 2 billion light-years from Earth, contains a supermassive black hole that appears to be moving at over 2,000 kilometers per second relative to its host galaxy, likely the result of an asymmetric black hole merger that occurred millions of years ago. The aftermath of such events can persist for hundreds of millions of years, as the displaced black hole gradually settles into a new equilibrium with its galactic environment. During this period, the galaxy's structure remains disturbed, its spiral arms distorted, its central star formation regions disrupted. It's as if the galaxy has been struck by a cosmic hurricane, its orderly rotation replaced by turbulent flows that take eons to subside. But supermassive black hole mergers represent only one category of cosmic violence in our survey of the universe's deadliest objects. Even more spectacular and potentially more dangerous are the phenomena that occur when black holes interact with other extreme objects, such as neutron stars, white dwarf stars, or even ordinary main sequence stars that venture too close to these gravitational monsters. When a black hole captures a companion star in a close orbit, the interaction creates some of the most energetic and unpredictable phenomena in the universe. The star's outer layers are gradually stripped away by tidal forces, forming streams of hot gas that spiral inward toward the black hole's event horizon. This process, known as Roche lobe overflow, can continue for millions of years, with the black hole slowly consuming its stellar companion like a cosmic vampire. The material stripped from the companion star doesn't fall directly into the black hole. Instead, it forms an accretion disk, a swirling maelstrom of superheated plasma that can extend for millions of kilometers around the black hole. Within this disk, magnetic field lines become twisted and compressed by the differential rotation, storing enormous amounts of energy that can be released suddenly in explosive magnetic reconnection events. These accretion disk instabilities can trigger what astronomers call X-ray bursts, sudden releases of high-energy radiation that can increase the system's brightness by factors of thousands or millions in a matter of seconds. The energy released in a single burst can exceed the total energy output of our Sun over several years, all concentrated into a beam of hard X-rays and gamma rays that can sterilize any planets within hundreds of light years. But even X-ray bursts pale in comparison to the cosmic catastrophe that occurs when a black hole completely disrupts its stellar companion. This process, known as a tidal disruption event, represents one of the most violent phenomena in the universe, capable of releasing more energy than a supernova explosion while creating conditions so extreme that they challenge our understanding of fundamental physics. The tidal disruption begins when a star approaches within what astronomers call the tidal radius of a black hole, the distance at which the gravitational gradient becomes so steep that it overcomes the star's own gravitational self-attraction. For a solar mass star approaching a million solar mass black hole, this critical distance is approximately 50 times the radius of our Sun, well outside the black hole's event horizon. As the star crosses this invisible boundary, it begins to stretch along the direction of the black hole's gravitational field. The side of the star facing the black hole experiences a much stronger gravitational pull than the far side, creating tidal forces that gradually overcome the electromagnetic forces holding the star together. Like taffy being pulled apart, the star elongates into a thin stream of plasma that wraps around the black hole in increasingly tight spirals. The disruption process is not gentle or gradual. Once tidal forces overcome the star's structural integrity, the disruption proceeds catastrophically, tearing the star apart in a matter of hours. Roughly half of the stellar material gains enough energy to escape the black hole entirely, flying off into space at velocities exceeding several thousand kilometers per second. The other half remains gravitationally bound, forming a long stream of debris that continues to orbit the black hole while gradually spiraling inward. As this debris stream settles into an accretion disk, the collision and friction between different parts of the stream heat the material to temperatures exceeding 10 million degrees Celsius. The entire system becomes a brilliant source of X-ray and ultraviolet radiation, often outshining the rest of its host galaxy for months or years. The energy output can reach 10 to the 44 watts, roughly equivalent to the brightness of 1,000 typical galaxies. But tidal disruption events are not just spectacular light shows. They represent genuine threats to life across vast regions of space. The high-energy radiation released during the disruption and subsequent accretion can strip away the atmospheres of planets located hundreds or thousands of light-years from the event. The particle streams accelerated by the black hole's magnetic field can create radiation environments so hostile that complex chemistry becomes impossible across entire stellar systems. Perhaps most concerning is our growing realization that tidal disruption events may be far more common than previously believed. Recent surveys have discovered dozens of these events in nearby galaxies, suggesting that they occur roughly once every 10,000 years in a typical galaxy. Given that the observable universe contains hundreds of billions of galaxies, this implies that somewhere in the cosmos, a star is being torn apart by a black hole approximately once every few minutes. This statistical reality adds a sobering perspective to our cosmic voyage. As we sit here contemplating these distant monsters, somewhere in the universe, perhaps in a galaxy whose light hasn't even had time to reach us yet, a star not unlike our own sun is experiencing its final moments, stretched and torn by gravitational forces beyond imagination, while its plasma streams spiral toward an event horizon from which no information can ever return. The debris from that distant stellar death will eventually be consumed by the black hole, adding infinitesimally to its mass and spinning up its rotation slightly. The energy released will propagate outward as electromagnetic radiation and high-energy particles, carrying news of the destruction across light-years of space. Some of that energy might eventually reach our own solar system, arriving as a faint whisper of high-energy photons that will strike our upper atmosphere and decay harmlessly into shower particles, the last messenger from a star that died in violence billions of years ago. These tidal disruption events also serve as cosmic laboratories, allowing us to study the behavior of matter under conditions that cannot be replicated anywhere else in the universe. The temperatures, pressures, and magnetic field strengths achieved during stellar disruption exceed anything we can create artificially, providing unique insights into fundamental physics and the behavior of matter in extreme environments. As we observe these cosmic laboratories from our distant vantage point, we're witnessing physics pushed beyond the boundaries of terrestrial experience into realms where the familiar laws that govern our daily lives undergo fundamental transformations. The plasma created during stellar disruption achieves densities and temperatures that exist nowhere else in the universe, except perhaps in the cores of the most massive stars during their final moments of collapse. Within the debris stream of a tidally disrupted star, individual atoms cease to exist as discrete entities. The temperatures are so extreme that electrons are stripped away from their nuclei, creating a soup of charged particles that behaves more like a fluid than a gas. This plasma becomes threaded with magnetic field lines of incredible intensity, fields millions of times stronger than Earth's magnetic field, capable of accelerating particles to energies that rival the most powerful cosmic rays. But tidal disruption events represent just one manifestation of the deadly phenomena that surround active black holes. Even more extreme are the relativistic jets that some black holes launch into space. cosmic blowtorches that extend for hundreds of thousands of light-years while maintaining their coherence and power across distances that dwarf entire galactic clusters. These jets represent one of the most mysterious and dangerous aspects of black hole physics. They form when material from the accretion disk is somehow channeled along the black hole's rotation axis and accelerated to velocities exceeding 99% the speed of light. The exact mechanism behind this acceleration remains one of astrophysics' greatest puzzles, but the effects are undeniably real and spectacularly violent. The material in these jets consists primarily of electrons and positrons, matter and antimatter particles that have been accelerated to such extreme energies that they behave more like pure energy than conventional matter. When these particles interact with magnetic fields or collide with ambient gas in space, they produce radiation across the entire electromagnetic spectrum, from radio waves to gamma rays of such high energy that they can penetrate straight through the Earth without being absorbed. For any civilization unfortunate enough to be located in the path of one of these jets, the consequences would be immediate and fatal. The high-energy radiation would arrive at the speed of light, providing no warning of the approaching catastrophe. Within minutes, the planet's atmosphere would be stripped away by the intense particle bombardment, while the surface would be sterilized by gamma-ray doses thousands of times higher than anything that could support life. But perhaps most terrifying is the realization that these jets can remain active for millions or even billions of years, creating zones of destruction that persist across cosmic timescales. The black hole at the center of the galaxy Centaurus A has been launching a jet for at least 10 million years, creating a cavity in the surrounding intergalactic medium that extends for over 1 million light-years. Any star system that happened to be born in the path of this jet during its long active phase would find itself in a radiation environment completely hostile to the development of complex chemistry, let alone life. The energy requirements for maintaining these jets challenge our understanding of how black holes can extract energy from their surroundings. The total power output can exceed 10 to the 40 watts, equivalent to the brightness of thousands of galaxies, all channeled into beams narrow enough to maintain their coherence across intergalactic distances. This energy must ultimately come from the black hole itself, either from the gravitational potential energy of infalling matter or from the rotational energy of the black hole's spin. Recent theoretical work suggests that the most powerful jets may be extracting energy directly from the black hole's rotation through a process called the Penrose mechanism. In this scenario, magnetic field lines threading the black hole's ergosphere become twisted by the dragging of space-time, building up enormous tensions that eventually snap like cosmic rubber bands, launching material outward at relativistic speeds while simultaneously slowing the black hole's rotation. This energy extraction process represents one of the most efficient engines in the universe, capable of converting up to 42% of a black hole's mass energy into usable work. For comparison, nuclear fusion, the process that powers stars, converts less than 1% of mass into energy. The implications are staggering. A black hole jet represents nature's ultimate power source, an engine of cosmic destruction that operates with an efficiency that makes our most advanced technology seem primitive by comparison. But jets are not the only way that black holes project their deadly influence across vast distances. Some of the universe's most extreme objects are magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's, that can create conditions so violent they challenge the basic structure of matter itself. When these objects fall into black holes, the results are catastrophic beyond imagination. The magnetic field lines of a magnetar, already twisted into configurations of unimaginable complexity, become further distorted as they approach the black hole's event horizon. The differential rotation of the accretion disk winds these fields into increasingly tight spirals, building up magnetic tensions that eventually exceed the binding energy of atomic nuclei. When these field lines reconnect, they release energy bursts that can briefly outshine entire galaxies. These magnetic reconnection events, known as magnetospheric substorms, create particle acceleration mechanisms so efficient that they can boost electrons and protons to energies exceeding those produced by the most powerful particle accelerators on Earth by factors of millions. The resulting cosmic ray flux can sterilize entire regions of space, creating dead zones where complex molecules cannot survive the constant bombardment of high-energy particles. Even more exotic are the theoretical objects known as primordial black holes, remnants from the very early universe that may have formed directly from density fluctuations in the primordial plasma. These objects, if they exist, could have masses ranging from microscopic scales up to thousands of solar masses, and their evaporation through Hawking radiation could create some of the most violent explosions in cosmic history. Stephen Hawking's theoretical prediction that black holes should slowly evaporate by emitting radiation suggests that the smallest primordial black hole holes should have completely evaporated by now, releasing their entire mass energy in final explosive bursts comparable to millions of hydrogen bombs. Larger primordial black holes would still be evaporating today, creating steady streams of high-energy particles that could serve as natural particle accelerators distributed throughout the galaxy. The search for these evaporating black holes has so far been unsuccessful, but their potential discovery would revolutionize our understanding of both cosmology and particle physics. The radiation they emit during evaporation includes particles that cannot be produced by any other known process, potentially providing insights into physics beyond the standard model of particle physics. But perhaps the most disturbing aspect of our survey of cosmic violence is the growing realization that we may be living in a cosmic shooting gallery, surrounded by potential threats that operate on timescales so long that human civilization has not existed long enough to witness their full cycles of activity. The supermassive black holes that appear quiescent today may simply be between feeding episodes, sleeping giants that could reawaken at any time if fresh material becomes available. Consider our own galactic center, where Sagittarius A star sits apparently dormant, occasionally snacking on small gas clouds but showing none of the violent activity characteristic of active galactic nuclei. Yet geological evidence suggests that this object may have been far more active in the recent past, possibly as recently as a few million years ago. Isotope ratios in deep ocean sediments hint at periods of increased cosmic ray bombardment that could be explained by outbursts from our galaxy's central black hole. If Sagittarius A star were to suddenly begin feeding actively, perhaps by capturing a large molecular cloud or experiencing an influx of material from a stellar disruption event, the consequences for life on Earth could be severe. The increased radiation environment would affect our planet's upper atmosphere, potentially depleting the ozone layer and exposing the surface to harmful ultraviolet radiation. High-energy cosmic rays accelerated by the active galactic nucleus could trigger increased mutation rates in living organisms, potentially affecting the course of evolution itself. These possibilities highlight one of the most unsettling aspects of black hole physics: their capacity for sudden, unpredictable outbursts that can affect entire galactic environments. Unlike stars, whose evolution proceeds according to well-understood nuclear physics over predictable timescales, black holes can remain dormant for millions of years and then suddenly flare to life when fresh fuel becomes available. The stochastic nature of black hole feeding makes them particularly dangerous from a cosmic perspective. There is no way to predict when a quiescent supermassive black hole might suddenly begin an active phase. No early early warning system that could alert distant civilizations to prepare for the coming radiation storm. The first sign of renewed activity would be the arrival of high-energy photons traveling at the speed of light, providing no opportunity for preparation or defense. This unpredictability extends to stellar mass black holes as well, particularly those in binary systems where they slowly accrete material from companion stars. These systems can remain stable for millions of years, with the black hole consuming material at a steady, predictable rate. But small perturbations in the orbit, perhaps caused by the gravitational influence of a passing star, can suddenly destabilize the system, triggering catastrophic mass transfer events that flood the black hole with more material than it can process smoothly. The result is a series of X-ray outbursts that can increase the system's brightness by factors of millions, creating radiation environments that would be lethal to any complex life forms within hundreds of light years. These outbursts can last for weeks or months, long enough to cause permanent damage to planetary atmospheres and biospheres across vast regions of space. As our cosmic journey continues deeper into the realm of gravitational monsters, we begin to encounter objects that exist at the very limits of what the laws of physics allow. These are black holes, so massive, so dense, and so energetic that they approach fundamental boundaries imposed by quantum mechanics and general relativity, boundaries beyond which our current understanding of nature simply breaks down. At these extreme boundaries, we encounter black holes that challenge not merely our technological capabilities or our ability to survive their influence, but our fundamental understanding of what reality itself means. These are objects where the familiar concepts of space and time, cause and effect, even the basic notion of information and its conservation, become twisted into forms that would be unrecognizable to anyone anchored in everyday experience. The most massive black holes we have discovered approach what theorists call the fundamental mass limit, a boundary beyond which the very concept of a black hole may cease to have meaning. This limit, estimated to be somewhere around 50 to 100 billion solar masses, emerges from the intersection of quantum mechanics and general relativity, two theories that normally operate in completely separate domains but converge in the extreme environments around the most massive gravitational objects. At these scales, the event horizon of a black hole becomes so large that its circumference approaches the size of the observable universe itself when viewed from certain reference frames. The concept of locality, the idea that objects can only influence their immediate surroundings, begins to break down completely. Information falling into such a black hole might become distributed across regions of space so vast that cause and effect relationships become meaningless, creating paradoxes that strike at the heart of physical law. Consider the black hole candidate TON 618, located over 10 billion light-years from Earth in the constellation Canes Venatici. This monster contains an estimated 66 billion times the mass of our Sun, making it one of the most massive objects ever discovered. Its event horizon has a diameter of approximately 800 billion kilometers, roughly 5,000 times the distance from Earth to the Sun. To put this in perspective, light would take nearly 3 days to travel from one side of this black hole's event horizon to the other. The gravitational influence of such an object extends across cosmological distances. Its effects on space-time curvature can be detected hundreds of millions of light-years away, making it a significant source of gravitational lensing that distorts our view of more distant galaxies. The object acts like a cosmic magnifying glass, bending light from background objects and creating multiple images of the same distant galaxy scattered across the sky. But TON 618 represents more than just an extreme example of cosmic engineering. It exists in a state that may be fundamentally unstable according to some interpretations of quantum gravity. Recent theoretical work suggests that black holes approaching the fundamental mass limit may undergo spontaneous fragmentation, breaking apart into smaller objects through processes that have no analog in classical physics. This fragmentation would not be a gentle dispersal of matter back into space. Instead, it would represent a catastrophic phase transition, similar to the way water suddenly transforms into steam when heated beyond its boiling point. The energy released during such an event would exceed that of the Big Bang itself, creating a cosmic explosion capable of sterilizing entire galactic clusters and potentially affecting the structure of space-time across billions of light-years. The possibility that the largest black holes might be inherently unstable adds a new dimension of cosmic dread to our survey of the universe's deadliest objects. These are not merely dangerous because of what they do to their immediate surroundings, but because their very existence might represent a kind of cosmic time bomb, a fundamental instability in the fabric of reality that could trigger consequences affecting the entire observable universe. Even more disturbing is the realization that we have no way to predict when such an event might occur. The quantum processes that govern black hole stability operate on timescales that can range from microseconds to trillions of years, with no way to determine which regime applies to any particular object. A supermassive black hole could exist peacefully for billions of years and then suddenly undergo catastrophic fragmentation without any warning signs visible to distant observers. This uncertainty extends to our understanding of what happens when black holes of comparable mass collide and merge. While we have detected gravitational waves from stellar mass black hole mergers, the collision of two supermassive black holes containing tens of billions of solar masses each would create gravitational wave bursts of such intensity that they could potentially damage the structure of space-time itself. The merger would begin millions of years before the actual collision as the two objects spiral toward each other while losing energy to gravitational wave radiation. During this approach phase, both black holes would likely be feeding actively, their accretion disks interacting in complex ways that could trigger unprecedented outbursts of electromagnetic radiation. The combined system would become the brightest object in the universe, visible across the entire observable cosmos. As the black holes approach within light hours of each other, their individual event horizons would begin to merge and distort, creating regions where the normal concepts of inside and outside become meaningless. The space-time around the system would become so severely warped that light rays could become trapped in stable orbits, creating a cosmic hall of mirrors where the same photon might circle the system hundreds of times before finally escaping. In the final seconds before merger, the gravitational wave emission would reach intensities that challenge the fundamental structure of space and time. The energy flux would exceed the critical threshold at which vacuum fluctuations can spontaneously create particle pairs, potentially filling the space around the merger with a plasma of electrons and positrons created directly from the quantum vacuum. The moment of merger itself would create gravitational waves so powerful that they could be detected by hypothetical observers located anywhere in the observable universe. The energy released in gravitational waves alone would exceed the rest mass energy of several solar systems, all radiated away in the form of space-time distortions that propagate outward at the speed of light. But the most terrifying aspect of such an event would be its potential to trigger a cascade of similar mergers throughout the universe. The gravitational wave burst from one supermassive black hole merger could perturb other massive black hole systems, potentially destabilizing their orbits and triggering additional mergers in a cosmic chain reaction that could reshape the large-scale structure of the universe. This possibility has led some theorists to speculate about the existence of cosmic epochs dominated by black hole violence, periods in the universe's history when cascading merger events create conditions so extreme that normal stellar and galactic evolution becomes impossible. During such epochs, the universe would be filled with gravitational wave radiation at intensities that could prevent the formation of stable planetary systems, making the development of complex life impossible across vast regions of space and time. Evidence for such violent epochs might already exist in the cosmic microwave background, the afterglow radiation from the Big Bang that still fills the universe today. Subtle patterns in this radiation could preserve the signatures of ancient gravitational wave storms, providing clues about cosmic violence that occurred when the universe was young and black holes were more numerous and active than they are today. The study of these primordial gravitational wave signatures represents one of the most active frontiers in modern cosmology, with new space-based detectors planned to search for evidence of cosmic violence dating back to within seconds of the Big Bang itself. These observations could reveal whether the universe has always been as relatively peaceful as it appears today, or whether we are living in a temporary lull between epochs of cosmic catastrophe. But even as we probe deeper into these theoretical extremes, we must remember that the deadliest black holes in the universe are not merely abstract mathematical objects or distant threats to hypothetical civilizations. They are active participants in the cosmic ecosystem, integral components of the processes that create and destroy galaxies, regulate star formation, and ultimately determine whether conditions suitable for life can exist anywhere in the universe. The supermassive black holes at galactic centers serve as cosmic regulators, their feeding patterns and energy output controlling the rate at which new stars form throughout their host galaxies. When they feed actively, their radiation and particle jets heat the surrounding gas to temperatures that prevent it from cooling and condensing into new stellar nurseries. When they become quiescent, star formation rates can increase dramatically, potentially exhausting a galaxy's gas reserves in a cosmic feeding frenzy that leaves it unable to sustain further stellar birth. This regulatory role makes supermassive black holes essential components of galactic evolution, cosmic thermostats that maintain the delicate balance between stellar birth and death across billions of years. Without them, galaxies would either burn through their gas supplies too quickly, leaving the universe filled with dead stellar remnants, or remain too cold and diffuse to support the dense stellar environments necessary for the formation of heavy elements. The heavy elements created in stellar cores and dispersed by supernova explosions provide the raw materials for rocky planets and ultimately for the complex chemistry that enables life. The regulation of this process by supermassive black holes means that these cosmic monsters are indirectly responsible for the existence of every carbon atom in our bodies, every oxygen molecule we breathe, every silicon chip in our electronic devices. This intimate connection between destruction and creation, between cosmic violence and the conditions necessary for life, represents one of the most profound paradoxes in our understanding of the universe. The deadliest objects in existence are simultaneously the enablers of everything we hold dear, the cosmic gardeners whose violent pruning allows the universe to bloom with the complexity necessary for consciousness to emerge and contemplate its own existence. As we prepare to venture even deeper into the realm of gravitational extremes, we approach objects that exist at the very edge of detectability, black holes so distant or so exotic that they push our observational capabilities to their absolute limits. These are the cosmic phantoms, objects whose existence we can barely confirm, but whose influence on the universe may be more profound than anything we have yet discovered. These cosmic phantoms lurk at the very boundaries of observation and theory, existing in states so extreme that they challenge not only our instruments but our fundamental concepts of what it means for an object to exist at all. They are the black holes that hide behind veils of dust and gas, objects so deeply embedded in cosmic debris that their presence can only be inferred from the subtle gravitational dances of nearby matter, the slight perturbations in stellar orbits, or the mysterious heating of gas clouds light years away from any visible source. Among these hidden monsters are what astronomers call obscured active galactic nuclei, supermassive black holes surrounded by such thick cocoons of dust that virtually no optical light escapes from their immediate vicinity. These objects can be feeding voraciously, consuming matter at rates exceeding several solar masses per year, yet remain completely invisible to conventional telescopes. They announce their presence only through hard X-rays that manage to penetrate their dusty shrouds, or through the faint infrared glow of dust grains heated to incandescence by the hidden furnace at their core. The galaxy NGC 1068, located approximately 160 million light-years from Earth, harbors one of these phantom feeders. From visible light observations, it appears to be a relatively quiet elliptical galaxy, showing little sign of the violent activity typically associated with active supermassive black holes. Yet observations at infrared and X-ray wavelengths reveal the presence of a monster consuming matter at a rate that should make it one of the brightest objects in the local universe. The black hole at the center of NGC 1068 is hidden behind a torus of dust and gas so dense that it absorbs over 99% of the optical and ultraviolet radiation produced by the accretion process. This material, heated to temperatures exceeding 1000 degrees by the absorbed radiation, glows brightly in the infrared, creating the cosmic equivalent of a cloaked predator whose body heat gives away its position despite its visual invisibility. What makes these obscured systems particularly dangerous is their unpredictability. Because we cannot directly observe their feeding patterns or energy output, we have no way to predict when they might undergo dramatic changes in activity. The dusty shrouds that hide them from view also make it impossible to monitor the stability of their accretion disks or the buildup of magnetic field energy that could trigger sudden outbursts. When such an object does flare to life, clearing away its obscuring material through radiation pressure or explosive events, the results can be spectacular and terrifying. The hidden monster suddenly becomes visible, appearing to brighten by factors of thousands or millions as its true energy output is finally revealed. Any civilizations located within the radiation cone of such an event would face immediate sterilization with no advance warning beyond the arrival of the deadly photons themselves. Even more mysterious are the intermediate mass black holes, objects that occupy the poorly understood middle ground between stellar mass black holes and supermassive giants. These cosmic enigmas, if they exist in the numbers suggested by some theoretical models, could represent a vast hidden population of gravitational monsters distributed throughout galactic halos and star clusters, invisible to current detection methods, but capable of sudden, devastating interactions with normal matter. The difficulty in detecting intermediate mass black holes stems from their size and feeding patterns. Too small to power the brilliant quasars associated with supermassive black holes, yet too large to be easily identified through the gravitational wave signatures characteristic of stellar mass mergers. They exist in a detection gap that leaves vast uncertainties about their numbers and distribution throughout the universe. Recent observations have hinted at the existence of these objects through their gravitational effects on surrounding star clusters and gas clouds. The globular cluster 47 Tucanae shows evidence of a dark central mass containing several thousand times the mass of our Sun, while the star cluster MGG11 contains stars moving at velocities that can only be explained by the presence of a black hole containing tens of thousands of solar masses. If intermediate mass black holes are as common as some models suggest, they could represent one of the most significant hidden threats in our galactic neighborhood. Unlike supermassive black holes, which are confined to galactic centers and announce their presence through spectacular electromagnetic displays, intermediate mass black holes could be wandering freely through space, invisible until the moment they encounter and destroy whatever unfortunate matter happens to cross their path. The possibility that such objects could be moving through our own galactic region, following eccentric orbits that carry them far from their birth sites, adds a disturbing element of randomness to cosmic safety. A wandering intermediate mass black hole passing through the outer regions of our solar system could gravitationally disrupt the orbits of comets in the Oort cloud, sending a devastating shower of icy projectiles toward the inner planets with little advance warning. Even more exotic are the theoretical objects known as primordial black holes, relics from the very early universe that could exist at virtually any mass scale from microscopic to stellar proportions. These objects, if they exist, would have formed not from stellar collapse, but from direct gravitational collapse of density fluctuations in the primordial plasma that filled the universe during its first moments. The mass spectrum of primordial black holes depends sensitively on the exact conditions that existed during the universe's inflationary epoch, a period of exponential expansion that occurred within the first fraction of a second after the Big Bang. Small variations in the strength or duration of inflation could have led to the formation of primordial black holes, with masses ranging from subatomic scales up to hundreds of thousands of solar masses, creating a hidden population of gravitational objects distributed throughout the universe according to patterns that we are only beginning to understand. The smallest primordial black holes, those with masses comparable to asteroids or mountains, would have completely evaporated by now through Hawking radiation, releasing their entire mass energy in explosive bursts that could have contributed to the high-energy cosmic ray background observed throughout the galaxy. Larger primordial black holes would still be evaporating today, creating point sources of high-energy radiation scattered randomly throughout space. The search for these evaporating black holes has become one of the most intriguing frontiers in observational astronomy, with space-based gamma-ray telescopes scanning the sky for the characteristic signature of black hole evaporation. The discovery of even a single evaporating primordial black hole would revolutionize our understanding of the early universe while providing direct observational evidence for some of the most exotic predictions of quantum gravity. But perhaps most disturbing are the theoretical possibilities that emerge when we consider black holes that might exist in higher dimensional space, objects whose gravitational influence could extend into dimensions beyond the three spatial dimensions of our everyday experience. According to some interpretations of string theory and other theories of quantum gravity, black holes could be fundamentally higher dimensional objects, with only their three-dimensional shadows visible to observers confined to our familiar spacetime. These higher dimensional black holes could possess properties that seem impossible from our limited perspective, including the ability to appear and disappear suddenly as they move through dimensions we cannot perceive, or to exert gravitational influences that seem to violate conservation laws when viewed from our three-dimensional vantage point. Their true size and mass could be vastly greater than what we observe, making them far more dangerous than conventional analysis would suggest. The possibility that some of the unexplained gravitational anomalies observed in our galaxy, such as the mysterious dark matter that seems to outweigh ordinary matter by factors of 5 to 1, might actually be evidence of higher dimensional black holes has led to intense theoretical investigation. If even a small fraction of dark matter consists of such exotic objects, their interactions with ordinary matter could create phenomena that we are only beginning to recognize and understand. Recent advances in gravitational wave astronomy have opened new possibilities for detecting these exotic objects through their merger signatures. Higher dimensional black holes should produce gravitational wave patterns that differ subtly but detectably from those created by conventional three-dimensional mergers, providing a potential observational test of theories that extend beyond our familiar spacetime. The implications of discovering higher dimensional black holes would extend far beyond astronomy and astrophysics, potentially revealing that our entire universe is embedded in a larger, more complex reality whose true nature we have barely begun to glimpse. The deadly objects we have been cataloging throughout our cosmic journey might represent only the visible fraction of a vast population of gravitational monsters whose full extent and capabilities remain hidden in dimensions beyond our current perception. As we push deeper into these theoretical realms, we encounter objects that exist at the intersection of black hole physics and cosmology itself, regions where the distinction between individual objects and the structure of spacetime becomes meaningless. These are the cosmic horizons, boundaries in space and time beyond which information cannot propagate, creating regions of the universe that are forever hidden from observation regardless of how advanced our technology becomes. The cosmological event horizon represents the ultimate boundary of observability, a spherical surface centered on Earth beyond which light emitted today will never reach us due to the accelerating expansion of the universe. Objects beyond this horizon exist in a state of permanent isolation from our local region of spacetime, their evolution proceeding according to physical laws we can theorize about but never directly observe. Within this cosmic horizon there may exist black holes of unimaginable size and power, objects so massive that they approach the scale of the observable universe itself. These cosmic-scale black holes would represent the ultimate expression of gravitational dominance, regions where the curvature of spacetime becomes so extreme that the concepts of space and time themselves lose their familiar meanings. The existence of such objects would imply that our entire observable universe might be embedded within the event horizon of an unimaginably massive black hole, making us cosmic prisoners trapped within a gravitational well whose true scale dwarfs our wildest imaginations. This possibility, while speculative, emerges naturally from certain solutions to Einstein's field equations and represents one of the most profound challenges to our understanding of cosmic structure and our place within it. This possibility that our entire cosmos might exist within some vast gravitational prison leads us to contemplate even more disturbing scenarios, where the deadliest black holes are not distant threats but intimate components of the very fabric of reality we inhabit. If the universe itself is bounded by an event horizon of unimaginable scale, then every moment of our existence unfolds within the grip of the ultimate gravitational monster, a black hole so vast that galaxies and galactic clusters serve as mere subatomic particles in its cosmic anatomy. The mathematics of such cosmic-scale black holes suggests that their internal structure would be utterly unlike anything we associate with smaller gravitational objects. Rather than containing a single point like singularity at the center, these universal-scale monsters might harbor entire pocket universes, regions of space-time where the laws of physics take on forms completely alien to our experience. Within such realms, time might flow backwards, space might have negative curvature, or matter might exist in states that violate every principle of thermodynamics we consider fundamental. But even as we grapple with these cosmological extremes, we must return our attention to the more immediate threats posed by the black holes we can actually observe and study. These objects, while perhaps not encompassing the entire universe, still possess the power to end civilizations, sterilize galactic regions, and fundamentally alter the course of cosmic evolution across vast scales of space and time. Among the most immediately dangerous are the black holes locked in what astronomers call death spirals with companion objects, systems where two massive gravitational monsters orbit each other in ever-tightening circles as they lose energy to gravitational wave radiation. These binary systems represent cosmic time bombs, slowly counting down toward merger events that will release more energy in seconds than most stars produce in their entire lifetimes. The binary system PSRB 1913+16, located approximately 21,000 light-years from Earth, provides a perfect example of this cosmic choreography of destruction. This system consists of two neutron stars, each containing approximately 1.4 times the mass of our Sun, compressed into spheres just 12 miles in diameter, orbiting each other every 2 hours and 24 minutes. The gravitational waves produced by this orbital dance carry away energy at a rate that causes the two objects to spiral inward by approximately 3.5 millimeters per year. This might seem like a glacially slow approach, but the mathematics are relentless. In approximately 300 million years, these two objects will collide in an event that will briefly outshine every star in the galaxy while releasing gravitational waves detectable across the entire observable universe. The collision itself will last only milliseconds, but in that brief span, the merger will convert approximately 1/10 of a solar mass directly into gravitational wave energy. The space-time distortions produced will be so intense that they could be detected by gravitational wave observatories located billions of light-years away, making the event visible across a significant fraction of the cosmos. But neutron star mergers represent only one category of these cosmic time bombs. Even more energetic are the binary systems containing black holes, particularly those where two stellar mass black holes spiral toward each other, or where a black hole slowly consumes a companion star through tidal disruption and accretion. The system known as GW150914, detected by the LIGO gravitational wave observatories, involved the merger of two black holes containing approximately 36 and 29 solar masses, respectively. The final moments of this cosmic collision converted 3 solar masses worth of matter directly into gravitational wave energy, creating space-time distortions that propagated across 1.3 billion years of cosmic history before reaching Earth. These stellar mass binary mergers, while spectacular, pale in comparison to the catastrophic events that occur when supermassive black holes collide. The approach phase of such mergers can last for hundreds of millions of years, with both objects likely feeding actively as their gravitational interaction disrupts surrounding gas clouds and stellar systems. The electromagnetic radiation produced during this extended courtship dance can make the combined system visible across the entire observable universe. As the supermassive black holes approach within light years of each other, their individual accretion disks begin to interact, creating complex shock patterns that can trigger unprecedented outbursts of high-energy radiation. The combined system becomes what astronomers call a binary active galactic nucleus, an object so energetic that it can regulate star formation throughout its entire galactic cluster, while simultaneously sterilizing vast regions of surrounding space. The final approach, when the black holes are separated by distances comparable to their own event horizons, occurs on timescales of hours or days. During this phase, the gravitational wave emission reaches intensities that challenge our understanding of space-time itself. The energy flux becomes so enormous that it could potentially create particle pairs directly from the quantum vacuum, filling the space around the merger with a plasma of electrons and positrons that glows with the heat of stellar cores. But perhaps most terrifying are the theoretical scenarios that emerge when we consider what happens if these binary mergers become unstable or asymmetric. Computer simulations suggest that certain configurations of merging black holes can produce gravitational wave kicks so powerful that they launch the merged object away from its host galaxy at velocities exceeding several thousand kilometers per second. These runaway black holes, containing billions of times the mass of our Sun and moving at speeds that could carry them across entire galactic clusters in just a few million years, represent perhaps the ultimate expression of cosmic danger. They are gravitational bullets fired by the universe itself, capable of wreaking havoc on any stellar system or galactic structure unfortunate enough to lie in their path. The galaxy 3C186 shows clear evidence of hosting such a runaway supermassive black hole. The central object appears to be displaced from the galaxy's geometric center and moving at over 2,000 kilometers per second relative to the surrounding stellar population. The displacement suggests that this black hole received a gravitational wave kick from an asymmetric merger that occurred sometime in the galaxy's recent past, launching it on a trajectory that will eventually carry it out of the galaxy entirely. If such a runaway black hole were to pass through a region like our local galactic neighborhood, the gravitational disruption would be catastrophic. The object's immense mass would perturb the orbits of countless stars, potentially ejecting planetary systems from their host stars or sending them plunging into their stellar cores. The tidal forces alone could trigger seismic activity on planetary surfaces, while the disruption of stellar orbits could destabilize the delicate gravitational balance that keeps galactic structure intact. Even more disturbing is the possibility that these runaway supermassive black holes might trigger cascade effects, their gravitational influence destabilizing other binary black hole systems and creating chain reactions of mergers and ejections that could fundamentally alter the structure of entire galactic clusters. The universe might be capable of experiencing episodes of gravitational chaos, periods when the normal, orderly evolution of cosmic structure gives way to violent reorganization driven by cascading black hole interactions. Evidence for such chaotic epochs might already exist in the large-scale structure of the universe, encoded in the statistical properties of galaxy distributions and the patterns of matter density that we observe today. Regions that appear to show deficit of massive galaxies or unusual clustering patterns might be the aftermath of ancient gravitational catastrophes, scars left by runaway black holes that disrupted normal galactic formation billions of years ago. The study of these patterns has become one of the most active frontiers in cosmology, with massive survey projects mapping the three-dimensional distribution of galaxies across billions of light-years in search of signatures of cosmic violence. These observations are revealing that the universe's large-scale structure shows subtle irregularities that could be explained by episodes of black hole-driven chaos, suggesting that gravitational monsters have been reshaping cosmic architecture throughout the entire history of the universe. But the influence of black holes on cosmic structure extends beyond dramatic merger events and runaway objects. Even quiescent supermassive black holes exert subtle but profound effects on their galactic environments, regulating star formation rates and determining the ultimate fate of entire stellar populations through processes that operate over billions of years. The supermassive black hole at the center of our own galaxy, Sagittarius A star, provides an excellent example of this regulatory influence. Despite appearing relatively inactive compared to the brilliant quasars powered by actively feeding black holes in distant galaxies, our galactic center black hole continuously influences star formation throughout the Milky Way through its gravitational effects and occasional feeding episodes. When Sagittarius A star does encounter fresh material, such as gas clouds or unlucky stars that wander too close to the galactic center, the resulting outbursts can affect conditions throughout the galaxy. High-energy radiation and accelerated particles propagate outward from the galactic center, heating intergalactic gas and potentially suppressing star formation in regions hundreds or thousands of light-years away. Geological evidence suggests that our planet has experienced several episodes of increased cosmic ray bombardment that might be linked to past outbursts from Sagittarius A star. Isotope ratios in deep ocean sediments show periodic spikes that could be explained by increased radiation from the galactic center, hinting that our own existence has been repeatedly influenced by the feeding patterns of the gravitational monster that anchors our galaxy. These connections between galactic center activity and planetary environments highlight one of the most unsettling aspects of black hole physics: their capacity to project deadly influence across timescales that dwarf human civilization. A single feeding episode lasting just a few thousand years could create radiation environments that persist for millions of years, affecting the evolution of life across countless worlds throughout the galaxy. The realization that supermassive black holes serve as cosmic regulators, determining which regions of the universe can support star formation and planetary development, transforms our understanding of habitability on cosmic scales. The universe is not a random collection of stars and planets where life can emerge anywhere conditions happen to be suitable. Instead, it is a carefully regulated system where supermassive black holes act as cosmic zoning authorities, determining which regions can support the complex chemistry necessary for biological evolution. This regulatory role makes the universe's deadliest objects simultaneously its most essential components, cosmic gardeners whose violent pruning enables the delicate balance between creation and destruction that allows complexity to emerge and persist over cosmic time scales. The paradox of cosmic gardening through destruction becomes even more profound when we consider the role these gravitational monsters play in seeding the universe with the heavy elements necessary for complex chemistry and, ultimately, life itself. The violent processes surrounding black holes, from stellar disruption events to the shockwaves generated by relativistic jets, create the extreme conditions necessary to forge elements that cannot be produced in the cores of normal stars. When a black hole's relativistic jet slams into surrounding gas clouds at velocities approaching the speed of light, the collision creates temperatures and pressures that rival those found in the cores of the most massive stars during their final moments of collapse. In these cosmic particle accelerators, protons and atomic nuclei are accelerated to energies so extreme that they can undergo nuclear reactions impossible under any other natural conditions. The result is a cosmic alchemy that transforms simple hydrogen and helium into the carbon, oxygen, silicon, and iron that form the building blocks of rocky planets and living organisms. Without these violent processes, the universe would remain forever locked in a state of primordial simplicity, filled with nothing but the lightest elements produced during the first few minutes after the Big Bang. But the black hole's role as cosmic alchemists extends beyond simply creating heavy elements. They also serve as the universe's mixing bowls, stirring and redistributing material across vast regions of space through their gravitational influence and energetic outflows. Material processed in the extreme environments near black holes gets ejected at high velocities, carrying enriched heavy element abundances to regions where new stars and planetary systems can form. The supernova explosions that create stellar mass black holes represent another crucial link in this cosmic recycling chain. The shock wave from a supernova not only disperses heavy elements created in the star's core, but also compresses surrounding gas clouds, triggering the formation of new stars that incorporate these heavier elements into their composition. Over cosmic time, this process gradually enriches the universe with the chemical complexity necessary for biological evolution. Yet even as we recognize the constructive role of these gravitational monsters, we cannot ignore the fact that their violent processes create zones of destruction that can persist for millions of years. The radiation and particle environments around active black holes are so extreme that they represent absolute barriers to the development of complex chemistry, let alone biological systems. Consider the environment around the supermassive black hole in the galaxy NGC 5548, located approximately 244 million light-years from Earth. This object is currently undergoing what astronomers call a tidal disruption event, slowly tearing apart a star that ventured too close to its event horizon. The process has been ongoing for over a decade, creating a persistent source of high-energy radiation that makes the black hole visible across electromagnetic wavelengths, from radio waves to hard X-rays. Any planetary system located within several thousand light-years of this event would be subjected to radiation doses that would sterilize surface conditions and strip away atmospheric protection. The high-energy photons would break apart complex organic molecules, while accelerated particles would trigger cascades of nuclear reactions in planetary atmospheres, creating radioactive isotopes that would remain dangerous for thousands of years after the initial radiation storm passed. The persistence of these deadly environments highlights one of the most challenging aspects of cosmic habitability: the universe's tendency towards sudden, unpredictable violence that can instantly transform previously safe regions into radiation-soaked death zones. Unlike terrestrial catastrophes, which typically affect only local regions and allow life elsewhere to continue evolving, cosmic violence operates on scales that can sterilize entire galactic regions simultaneously. This scale dependence creates what astronomers call the cosmic habitability paradox. While black holes are essential for creating the conditions necessary for life through their regulation of star formation and heavy element production, they simultaneously create exclusion zones where life cannot survive. The balance between these constructive and destructive influences determines whether any given region of the universe can support biological evolution over the billions of years necessary for complex life to emerge. Recent theoretical work suggests that this balance has changed throughout cosmic history, with the early universe being far more violent and hostile to life than the relatively quiet cosmos we observe today. During the universe's youth, when black holes were more numerous and active, the radiation background from quasars and active galactic nuclei may have been so intense that complex chemistry was impossible across vast regions of space. Only as the universe aged and expanded, diluting the density of active black holes and allowing their fuel supplies to become exhausted, did conditions become sufficiently calm for biological evolution to begin. This suggests that we might be living in a cosmic sweet spot, a period when the universe has become old enough for violence to subside, but not so old that all the fuel for star formation has been exhausted. But this cosmic tranquility may be temporary. As galaxies continue to merge and collide over cosmic time, their central supermassive black holes will eventually be brought into close proximity, triggering merger events that could reawaken the violent conditions of the early universe. The collision between our own Milky Way galaxy and the nearby Andromeda galaxy, predicted to occur in approximately 4.5 billion years, will bring together two supermassive black holes in a cosmic encounter that could dramatically alter conditions throughout our local galactic group. The merger of Sagittarius, a star, with Andromeda's central black hole, known as M31 star, would create a supermassive black hole containing over 8 million solar masses, making it one of the largest such objects in our local cosmic neighborhood. The gravitational waves produced by this merger would be detectable throughout the local group of galaxies, while the electromagnetic radiation could create a brief but intense quasar phase that would affect planetary environments across millions of light years. For any civilizations that might exist in our galactic region at that time, the Milky Way-Andromeda collision would represent an existential challenge requiring either evacuation to safer regions of space or the development of technologies capable of protecting entire worlds from radiation environments more intense than anything experienced in the past 5 billion years of terrestrial evolution. These long-term threats highlight the temporal dimension of black hole danger. The way these objects can remain dormant for millions or billions of years before suddenly reactivating in events that reshape entire galactic environments. Unlike stellar evolution, which proceeds according to predictable nuclear physics over well-understood timescales, black hole activity follows the stochastic rhythms of gravitational encounters and matter accretion, making it impossible to predict when quiescent objects might suddenly become deadly. This unpredictability extends even to objects we consider well understood. Recent observations of Sagittarius A star have revealed that our galaxy's central black hole experiences periodic flares of activity, sudden increases in brightness that suggest the capture and destruction of asteroidal or cometary material. While these events are relatively minor compared to full-scale stellar disruption events, they demonstrate that even apparently quiet black holes can undergo sudden changes in behavior. More concerning are the observations of so-called changing-look quasars, supermassive black holes that transition rapidly between active and quiescent states on timescales of years or decades rather than the millions of years predicted by conventional accretion models. These objects suggest that black hole feeding patterns may be far more variable and unpredictable than previously believed, with potentially dramatic implications for the stability of galactic environments. The changing look phenomenon appears to be triggered by instabilities in black hole accretion disks, sudden transitions between different accretion states that can cause dramatic changes in energy output within remarkably short periods. A black hole that has remained quiet for millions of years could potentially undergo a changing look transition and become an active galactic nucleus within a human lifetime, creating radiation environments that would affect entire galactic regions with minimal warning. These discoveries are forcing astronomers to reconsider fundamental assumptions about black hole behavior and cosmic habitability. The universe may be far more dynamically unstable than previously recognized, with black holes capable of sudden transitions between dormant and deadly states that could affect the development and survival of life across cosmic scales. The implications extend beyond immediate radiation threats to include more subtle but equally important effects on cosmic chemistry and star formation. When a supermassive black hole undergoes a sudden transition to active feeding, the energy output doesn't simply create a localized danger zone. Instead, it can trigger shockwaves that propagate throughout the intergalactic medium, heating gas clouds and preventing them from cooling sufficiently to form new stars. This suppression of star formation can persist for hundreds of millions of years after the initial outburst, creating extended periods when entire regions of the universe become unable to replace aging stellar populations. The result is a gradual dimming of affected regions as existing stars evolve and die without being replaced by new stellar births, eventually leaving behind galactic graveyards populated only by stellar remnants and failed stars. The cumulative effect of these processes over cosmic time suggests that black holes may be gradually sterilizing the universe, slowly reducing the number of regions capable of supporting complex chemistry and biological evolution. While new stars continue to form in regions shielded from black hole influence, the overall trend appears to be toward increasing cosmic sterility as supermassive black holes consume available fuel and their regulatory influence expands. This raises profound questions about the long-term habitability of the universe and the ultimate fate of any civilizations that might emerge during the current cosmic epoch. If black holes continue to grow and merge, eventually consuming or sterilizing most galactic environments, there may be fundamental limits to how long complex structures like technological civilizations can persist on cosmic scales. The prospect of cosmic sterilization through black hole dominance forces us to confront some of the deepest questions about our place in the universe and the ultimate meaning of consciousness in a cosmos increasingly dominated by gravitational monsters. If the long-term trend is toward expanding zones of destruction and diminishing opportunities for complex chemistry, then every moment of awareness, every scientific discovery, every work of art or act of love represents a temporary victory against the universe's inexorable slide toward gravitational tyranny. Yet even as we contemplate these cosmic timescales that dwarf human civilization, we must acknowledge that our understanding of black holes continues to evolve in ways that might completely transform our assessment of their role in cosmic evolution. The recent detection of gravitational waves has opened an entirely new window into black hole physics, revealing phenomena that were previously hidden from electromagnetic observation and challenging theoretical predictions that had stood unchallenged for decades. The merger events detected by LIGO and other gravitational wave observatories have revealed that stellar mass black holes can exist in binary systems with masses and spin rates that seem impossible according to conventional stellar evolution models. Some of the detected black holes are spinning so rapidly that they approach the theoretical maximum rotation rate, while others have masses that exceed what should be possible for objects formed from normal stellar collapse. These observations suggest that black holes may grow and evolve through processes we don't yet understand, potentially involving exotic physics that operates in the extreme gravitational environments near event horizons. The possibility that black holes might be able to violate conventional conservation laws or extract energy from sources other than conventional matter accretion opens up entirely new categories of cosmic violence that could operate on scales and timescales we haven't yet imagined. Consider the theoretical phenomenon known as black hole superradiance, a quantum mechanical process that allows rotating black holes to amplify electromagnetic or gravitational waves that interact with their ergospheres. Under certain conditions, this amplification could become unstable, creating runaway feedback loops that extract enormous amounts of energy from the black hole's rotation while generating particle beams or gravitational wave bursts of unprecedented intensity. If superradiant instabilities can occur in nature, they would create black holes that operate as cosmic lasers, coherently amplifying radiation fields until they reach intensities capable of affecting matter across intergalactic distances. The energy extraction could continue until the black hole's rotation is completely depleted, potentially converting a significant fraction of the black hole's mass energy into directed beams that propagate across the universe at the speed of light. Such events would represent the ultimate expression of cosmic violence, creating directed energy weapons of astronomical power that could sterilize entire galactic clusters while remaining completely unpredictable in their occurrence and direction. Any civilization unlucky enough to be located in the beam path of a super-radiant black hole would face annihilation so complete that no trace of their existence would survive. But superradiance represents only one of many exotic processes that might operate in the extreme environments around black holes. Recent theoretical work has suggested that the quantum vacuum near event horizons might be inherently unstable, capable of spontaneously creating particle pairs at rates that could dramatically alter black hole evolution and energy output. The Hawking radiation process, originally conceived as a slow evaporation mechanism that would cause black holes to gradually shrink over astronomical timescales, might actually be much more violent and unpredictable than initially believed. Quantum fluctuations near the event horizon could potentially trigger sudden bursts of particle creation that would cause black holes to undergo explosive mass loss events, releasing energy equivalent to multiple stellar explosions within timeframes of seconds or minutes. These quantum instabilities would be completely unpredictable, triggered by microscopic fluctuations that amplify through nonlinear feedback mechanisms until they reach macroscopic scales. A black hole that has remained stable for billions of years could suddenly undergo catastrophic evaporation without any external trigger, creating an explosion visible across the entire observable universe. The possibility that black holes might be fundamentally unstable on quantum scales adds an element of cosmic Russian roulette to the universe's long-term evolution. Rather than gradually growing larger and more dangerous over cosmic time, black holes might instead be slowly accumulating quantum instabilities that could eventually trigger chain reactions of evaporation events, filling the universe with high-energy radiation as the gravitational monsters that have shaped cosmic evolution for billions of years suddenly destroy themselves in spectacular fashion. Evidence for such quantum instabilities might already exist in the cosmic gamma-ray background, the diffuse radiation field that permeates space and whose origin remains partially mysterious. Some of this radiation could represent the afterglow of primordial black hole evaporation events that occurred when the universe was young and small. Black holes were more numerous than they are today. The search for signatures of black hole evaporation has become one of the most active frontiers in high-energy astrophysics, with space-based telescopes scanning the sky for the characteristic spectrum of gamma rays that would be produced by exploding black holes. The discovery of even a single evaporating black hole would revolutionize our understanding of quantum gravity while providing direct observational evidence that these gravitational monsters might not be as immortal as general relativity suggests. But perhaps most unsettling is the growing realization that black holes might interact with aspects of physics that remain completely unknown to current science. The conditions near black hole event horizons push physical theories into regimes where quantum mechanics and general relativity make conflicting predictions, suggesting that entirely new physics might emerge in these extreme environments. String theory and other approaches to quantum gravity predict that black holes might be connected to parallel universes or higher dimensional spaces through mechanisms that have no analog in our everyday experience. If such connections exist, black holes could serve as conduits for energy or information exchange with realms that exist beyond our three-dimensional space-time, making them potentially dangerous in ways that transcend conventional physics. The possibility that black holes might be doorways to other universes or dimensions transforms them from objects of cosmic destruction into cosmic mysteries whose true nature might be fundamentally incomprehensible from our limited three-dimensional perspective. They become not merely gravitational monsters that consume matter and energy, but cosmic interfaces that connect our reality to a larger multiverse whose structure and properties remain completely unknown. Recent theoretical work has suggested that some of the unexplained properties of dark matter and dark energy, the mysterious components that comprise over 90% of the universe's energy budget, might be explained by interactions with higher dimensional black holes whose full extent remains hidden from our observations. If this interpretation is correct, then the entire structure of our universe might be dominated by gravitational objects whose true scale and influence operate in dimensions we cannot perceive or measure. This possibility pushes the concept of cosmic danger beyond anything we can meaningfully quantify or predict. If black holes are higher dimensional objects that can manipulate our reality through mechanisms we don't understand, then their potential for causing harm extends far beyond radiation damage or gravitational disruption. They might be capable of altering the fundamental constants of physics, changing the properties of matter and energy in ways that could make our entire universe uninhabitable without warning. The search for evidence of higher dimensional physics has become one of the most challenging frontiers in theoretical physics, requiring mathematical tools and conceptual frameworks that push human understanding to its absolute limits. We are attempting to comprehend objects that might exist partially outside the spacetime we inhabit, using theories that describe realities we cannot directly experience or visualize. As we near the end of our cosmic journey through the realm of gravitational monsters, we find ourselves confronting the ultimate limitation of scientific knowledge: the possibility that the universe's deadliest objects operate according to principles that transcend human comprehension entirely. The black holes we have explored represent not just threats to life and civilization, but challenges to the very foundations of rational thought and scientific inquiry. They force us to confront the humbling possibility that consciousness, despite its remarkable ability to contemplate the cosmos, might be fundamentally limited in its capacity to understand the deepest truths about reality. The gravitational monsters that dominate our universe might operate according to logic so alien to human experience that even our most sophisticated theories provide only crude approximations to their true nature. Yet this limitation does not diminish the profound beauty and terror of our cosmic exploration. In contemplating these objects that exist at the boundaries of knowledge and possibility, we participate in one of the most remarkable phenomena in the known universe: the emergence of consciousness capable of pondering its own cosmic context, even when that context threatens to overwhelm our capacity for understanding. The deadliest black holes in the universe serve as cosmic mirrors, reflecting back our own limitations while simultaneously demonstrating the extraordinary achievement represented by any conscious being's attempt to comprehend the vast, violent, and mysterious cosmos that gave rise to awareness itself. The emergence of consciousness in a universe dominated by gravitational monsters represents perhaps the most improbable and precious phenomenon we have encountered in our cosmic journey. Here we are, collections of atoms forged in stellar cores and dispersed by supernova explosions, temporarily organized into patterns complex enough to contemplate the very forces that created and could destroy us. We exist in the brief interval between stellar birth and black hole dominance, in the narrow window of cosmic time when the universe is old enough for complexity to emerge, but young enough for stars to still shine. Every thought we think, every question we ask about black holes and cosmic violence represents a victory against the universe's tendency toward maximum entropy and gravitational collapse. We are the universe temporarily awakening to contemplate itself, patterns of information and awareness that have somehow emerged from the chaos of stellar explosions and gravitational interactions that define cosmic evolution. Yet our awareness comes with the sobering realization that we exist at the mercy of forces so vast and violent that they could erase every trace of human civilization without even registering our disappearance. The supermassive black hole at the center of our galaxy could undergo a sudden feeding episode tomorrow, flooding our region of space with lethal radiation. A gamma ray burst from a stellar collapse could sterilize our planet's surface within seconds. A wandering black hole could disrupt our solar system's delicate gravitational balance, sending Earth plunging into the sun or ejecting it into the frozen depths of interstellar space. These possibilities exist not as distant theoretical concerns, but as real physical processes operating continuously throughout the universe. Somewhere in the cosmos right now, as you contemplate these words, a star is being torn apart by tidal forces near a black hole's event horizon. Somewhere else, two black holes are spiraling toward a collision that will send gravitational waves rippling across space-time. In countless locations throughout the observable universe, matter is crossing event horizons from which no information can ever return, disappearing forever behind boundaries that separate the knowable from the unknowable. The scale of this ongoing cosmic violence is so vast that it challenges our ability to find meaning or purpose in our brief existence as conscious beings. What significance can human life possess when measured against forces that operate on scales of billions of years and billions of light years? How can our fleeting thoughts and feelings matter in a universe where entire galaxies can be sterilized by the outbursts of supermassive black holes? Yet perhaps the answer lies not in denying the universe's capacity for violence, but in embracing the remarkable fact that consciousness has emerged at all in such a hostile environment. We are not separate from the cosmic forces we have explored during our journey. We are manifestations of those same forces, temporary eddies in the flow of matter and energy that connects black holes to galaxies, galaxies to stars, and stars to the planets where life can emerge and evolve into awareness. The carbon in our bodies was forged in stellar cores and dispersed by supernova explosions. The oxygen we breathe was created in the heart of massive stars that ended their lives in catastrophic collapse, some of them forming the very black holes we have studied. The iron in our blood was synthesized in stellar furnaces, operating at temperatures and pressures that approach those found near event horizons. We are literally made of star stuff, animated by the same nuclear processes that power quasars and relativistic jets. This cosmic ancestry connects us intimately to the gravitational monsters we have encountered. The black holes that seem so alien and threatening are actually our cosmic relatives, objects formed by the same stellar evolution processes that created the heavy elements essential for biological chemistry. Without the violent deaths of massive stars, without the extreme conditions near black holes that forge and disperse heavy elements throughout space, the complex chemistry necessary for consciousness could never have emerged. In this sense, the deadliest objects in the universe are also our cosmic benefactors, the engines of creation that made our existence possible even as they threaten our continued survival. They represent the universe's capacity for both ultimate destruction and ultimate creativity, forces that can simultaneously sterilize entire galactic regions while seeding space with the raw materials necessary for future generations of stars, planets, and potentially life. The duality of creation and destruction embodied by black holes reflects a fundamental principle that operates throughout cosmic evolution. Nothing in the universe is purely constructive or purely destructive. The same supernova explosion that creates a black hole also disperses heavy elements essential for planet formation. The same gravitational forces that can tear matter apart at tidal boundaries also provide the energy that powers stellar fusion and enables the formation of complex molecular structures. This cosmic balance suggests that consciousness, rather than being an accidental byproduct of mindless physical processes, might represent a fundamental aspect of how the universe organizes and understands itself. Through our scientific investigations, our mathematical theories, and our aesthetic appreciation of cosmic beauty, we serve as the universe's mechanism for self-awareness, the means by which matter and energy achieve the capacity to contemplate their own existence and evolution. From this perspective, our cosmic journey through the realm of gravitational monsters becomes more than just an exploration of dangerous objects in distant space. It becomes an act of cosmic self-discovery, a process by which the universe, through our consciousness, comes to understand the forces that shape its own structure and evolution. Every equation we derive, every observation we make, every moment of wonder we experience while contemplating black holes represents the universe awakening to its own mathematical elegance and physical beauty. The fact that we can understand black holes at all, despite their extreme properties and alien nature, suggests a deep connection between the structure of consciousness and the structure of physical reality. Our mathematical theories successfully describe objects whose properties transcend direct human experience, implying that the patterns of thought that enable understanding are somehow matched to the patterns that govern cosmic evolution. This matching between mind and cosmos might not be coincidental. If consciousness is an emergent property of sufficiently complex information processing systems, and if the universe tends toward increasing complexity over cosmic time, then the emergence of awareness might be as inevitable as the formation of stars and galaxies. We might be witnessing not an accident of cosmic evolution, but one of its fundamental purposes, the development of systems complex enough to comprehend the forces that created them. The black holes we have studied during our journey, with their capacity to process and store information in ways that challenge our understanding of physics, might represent precursors or analogues to consciousness itself. The information paradoxes surrounding black hole evaporation, the complex feedback mechanisms that regulate their feeding patterns, and their role in organizing galactic structure all suggest that these objects operate as cosmic information processors on scales that dwarf any biological neural network. Perhaps consciousness and black holes are different manifestations of the same underlying cosmic tendency toward increasing complexity and information processing capability. While biological consciousness operates through electrochemical processes in neural networks, black holes might represent a form of gravitational consciousness that operates through space-time curvature and quantum field fluctuations near event horizons. This possibility transforms our relationship with these cosmic monsters from one of pure fear and fascination to something approaching kinship. If black holes are cosmic minds operating on scales of space and time that transcend biological existence, then our scientific study of them becomes a form of interspecies communication, an attempt to understand how consciousness manifests when it operates through gravitational rather than biological mechanisms. The messages these cosmic minds might be sending us through their gravitational wave emissions, their jet formations, and their complex feeding behaviors could contain insights into the nature of consciousness and reality that transcend anything achievable through purely terrestrial science. By learning to decode these signals, we might gain access to forms of knowledge that are literally astronomical in scope and significance. But whether or not black holes possess consciousness in any meaningful sense, our journey through their realm has revealed something profound about the nature of existence in a universe dominated by extreme gravitational forces. We have seen that the cosmos operates according to principles that transcend human intuition while remaining accessible to human reason. We have discovered that the most violent and dangerous objects in existence are simultaneously the most creative and essential components of cosmic evolution. Most importantly, we have learned that consciousness, wherever and however it emerges, represents something genuinely precious and remarkable in a universe that seems predominantly hostile to complex organization. The fact that we can contemplate black holes, derive equations that describe their behavior, and experience wonder at their alien magnificence demonstrates that the universe has achieved something genuinely extraordinary through the emergence of awareness. As we conclude our cosmic journey and return our attention to the small blue planet where consciousness has evolved the capacity to explore the universe's deadliest objects, we carry with us a transformed perspective on our place in the cosmic order. We are not separate from the gravitational monsters we have studied, but intimately connected to them through the deep structure of physical law and cosmic evolution. The black holes that seemed so threatening and alien when we began our journey have revealed themselves to be essential components of the cosmic ecosystem that made our existence possible. They are the sculptors of galaxies, the regulators of star formation, the creators of heavy elements, and the architects of the large-scale structure that defines our observable universe. Without them, the cosmos would be a cold, empty, lifeless place where consciousness could never emerge to contemplate its own cosmic context. In recognizing our deep connection to these gravitational monsters, we discover that consciousness is not an accident or an afterthought in cosmic evolution, but one of its most remarkable achievements. Through our capacity to understand and appreciate the universe's capacity for both creation and destruction, we participate in the cosmos's ongoing project of self-discovery and self-understanding. The deadliest black holes in the universe, far from being mere threats to our survival, are revealed to be our cosmic ancestors and teachers, objects whose violent beauty and alien majesty remind us of both our cosmic insignificance and our extraordinary privilege as conscious beings capable of contemplating the very forces that created us.